All right, Chemistry 3111. This is Chapter 18, which deals with aromatic substitution reactions. We're going to start with a set of reactions we call electrophilic aromatic substitution reactions. But if you think about benzene, and when we talked about aromatic rings in the last chapter, we think about an aromatic ring like benzene as being something that is just very stable, right? And we talked about why benzene is so stable. It has a Huckel number of electrons. It has a closed ring of p orbitals, right, that all overlap. Anyhow, with that in mind, you might think, well, benzene is completely unreactive, but in fact, that is not true, and that's what we're going to explore in this chapter. We're going to see a whole series of reactions where we're going to be able to substitute one group, like let's say a hydrogen, for example. We'll be able to substitute a hydrogen for something else, and that's called a substitution reaction. So if you remember earlier on when we were looking at alkene chemistry, right, we talked about a bromination reaction where if you take cyclohexene, which is this molecule right here, you treat it with bromine, and you end up doing an anti-addition of the bromines. And then, of course, you should be able to draw that mechanism, draw the bromonium ion, the nucleophilic attack, whatnot. So you would end up with this compound, and it's an enantiomer. Anyhow, but we said, okay, well, if you try to do the same type thing with benzene, benzene is not reactive. Okay, you're not going to get an addition reaction. And the reason why is because if you were to do that, both of those carbons in that green circle would be sp3 hybridized, and you would destroy the aromaticity of the six-membered ring, of the benzene ring. So what happens, though, and this is where it gets really interesting, is that if you introduce iron into the reaction, and I mean literal iron metal, if you just take some iron filing, let's say, and put it in the reaction, you actually end up with a substitution. Why do we call it substitution? Because you're substituting a hydrogen, right, which is here. You're removing the hydrogen and you're replacing it or substituting it with the bromine. So we have bromine and iron. So there must be some kind of effect that's occurring here that's causing this bromination or this substitution to occur. And this observed reaction is called an electrophilic aromatic substitution. Why? Because we're going to produce a powerful enough electrophile that our aromatic ring is going to behave as a nucleophile, right? We're going to take a pair of pi electrons and we can do a nucleophilic attack, anyhow, like this on a powerful enough electrophile. So we're going to look at a bunch of mechanisms where we see the aromatic ring behaving as a nucleophile and reacting with a variety of electrophiles. So what's the electrophile that's produced when we have bromine and iron mixed together? Well, we're going to answer that in a second. But before we do, let me take a second here to stop and show you the different types of electrophilic aromatic substitutions that we're going to look at in this chapter, right? Sometimes we call these EAS reactions. I don't do that a whole heck of a lot. But here we start with benzene, which again is a very stable molecule, but we're going to find that we can make electrophiles that are powerful enough to do a bromination, a chlorination, a nitration to install a nitro group, right? You should know what a nitro group is. The next one, this SO3H, that's a sulfonic acid. So a sulfonic acid. This one here, of course, is an alkyl group. So we're going to be able to install an alkyl group, and then this one here is an acyl group. Okay, an acyl group. Okay, so we're going to look at all of these different types of substitution reactions where we can add these different groups to the ring. And notice that the aromaticity of the ring is still intact. No matter which one of these substitutions we look at, we still have that six-membered ring with the alternating pi and sigma bonds. All right, well, let's get back into that halogenation of the alkene, right? This is something that we learned way back in the alkene chapter. That would be in Organic Chemistry 1. If you take the nucleophile here, which is cyclohexene, and you treat it with bromine. I don't know why this came out like this, but this should be a delta plus and a delta minus. So this should be delta plus, and this should be delta minus, like that. What happens is that when the nucleophile approaches the electrophile in the halogenation reaction, this addition reaction, the bromine becomes temporarily polarized, and so you end up with the nucleophile, the pi bond attacking that bromine that's partially positive, and of course you have a pair of electrons coming back here to form the bromonium ion, and you lose the bromide. And so again, this is organic chemistry 1, so I'm not going to reteach that in gross and dirty detail, but you end up with this, which is a bromonium ion, and then of course you end up with bromide, right? And then that acts as a nucleophile, and it can come in and attack from the opposite face of the ring like this. Anyhow, you get the idea. Well, what happens is when we take bromine, Br2, and we mix it with iron, we actually get a reaction occurring here between the iron and the bromine to make iron 3 bromide. So FeBr3, that's iron 3 bromide, right? You remember the stock naming system. And iron 3 bromide is a Lewis acid, and that is the catalyst that is required to make the bromine electrophilic enough. So what's the point here? The point is that when you did this reaction back in organic chemistry 1, it was just the polarizability of the bromine which rendered it electrophilic enough to react with the pi bond here. However, it's not electrophilic enough, bromine on its own, to just react with an aromatic ring. So we add the iron to make the Lewis acid catalyst, and that is what we're going to see is going to provide the electrophilic bromine that is required for the reaction to occur. So let me show you what happens. When the iron 3 bromide is in your reaction mixture, it's going to activate the bromine, making it even more electron poor. So remember, this is the catalyst that's produced. So we're not going to make a stoichiometric amount of this. We're just going to make some of this. Okay, so not all of the bromine is going to be converted into this, but we're going to have some of this present. Again, it is a catalyst. It is going to get recycled, and you'll see why. So here you have the iron 3 bromide, and it's reacting with the bromine, the Br2, and you end up with this species here where we have a positive charge on the bromine, but if the bromine takes the pair of electrons represented by that curved arrow, you end up with a bromine with a positive charge. You know, that's probably something we haven't even seen yet in general chemistry 1 or in organic chemistry 1, but now you're seeing it in organic chemistry 2, and you can imagine that if you have a bromine that's not a bromide, now you've got a bromine with a positive charge. It is hungry for electrons. It is starving for electrons, right? Remember, bromine is a halogen. Bromine wants to gain an electron to become isoelectronic with krypton. It doesn't want to lose electrons. So this guy is looking for electrons big time, right? What do we call something that's looking for electrons in organic chemistry? We call it an electrophile, right? Quite literally, an electron lover. So what happens when this electron lover or this electrophile is in the presence of an aromatic ring? Well, here's what happens. Remember, I told you the aromatic ring could behave as a nucleophile, and it does. So a pair of the pi electrons is going to come out, act as a nucleophile, and it's going to attack the bromine on the end of that complex that's formed between the iron 3 bromide and the bromine, like this. So we don't actually draw the mechanism showing the Br. We don't actually show this Br plus in the solution. What we actually show is this intermediate right here. Okay, so we show 2 arrows during the nucleophilic attack, like that. And then you form an intermediate. Now this intermediate is going to come up many, many, many times today and in this video. It's called a sigma complex. You see that the aromatic ring is destroyed, isn't it? There's no more aromaticity here, okay, because you've got an sp3 hybridized carbon, okay? But you see that there are 3 resonance contributors to the sigma complex, okay, and we can draw them all. But once we draw this one here, what we can show is that this intermediate here, okay, the iron with 4 bromines bound to it, one of the bromines is going to take the hydrogen to form HBr, which you can't really see on my slides. Okay, you see it over here on the far right. We regenerate the iron 3 bromide and we restore our aromatic ring. So we restore the aromatic ring and we also regenerate our catalyst. Pretty cool, huh? So if you can memorize this mechanism, and you have to memorize this mechanism, it's going to help you a lot, is what I mean to say, because it comes up so much. The exact same mechanism comes up over and over and over in this chapter. So what's step 1? Let's summarize. In the first step, the aromatic ring acts as an, it shouldn't say electrophile, it should say it acts as a nucleophile. So nucleophile, there we go. So the aromatic ring, sorry, I thought it said access, so it is correct. It attacks the electrophile, sorry. So the aromatic ring attacks the electrophile. You form the sigma complex, and then you just get a deprotonation of that sigma complex right here, and then you re-aromatize, right? You reform the aromatic ring. So you start with an aromatic ring, and you end with an aromatic ring, just like that. Now, if you might be thinking, well, come on, Mr. Dion, you've still, you told me that not all of the bromine is going to be gone because I'm only forming a catalytic amount of the iron 3 bromide. So why don't I get a reaction? Why don't I get an addition reaction with the bromine? Well, if you take a look at the reaction coordinate diagram, if you were to do an addition reaction to make this compound here, which we don't make, if you take a look at the free energy, right, the delta G, okay, on the y-axis here, and then we have our reaction coordinate at the bottom. The reaction is actually an endergonic reaction, okay, so the delta G would be positive in this case, whereas here, when you do the substitution, you actually end up with a negative delta G, okay? So it's an exergonic reaction. What do we mean? What does it mean? An exergonic reaction? It's going to be a spontaneous reaction, right? Because delta G is negative, whereas here delta G is positive. Okay, so just thinking about it in terms of Gibbs free energy and kind of answering that question, in case it's like burning inside you, like, why doesn't the addition happen? Well, that's why. All right. Anyhow, are there other Lewis acids that we could use besides iron 3 bromide? Yeah, absolutely. We can use aluminum tribromide. Remember, it's not aluminum 3 bromide because aluminum is in group 3A. It's not a transition metal, so it's just aluminum tribromide, Al, right? AlBr3. Well, that's also a good Lewis acid, isn't it? Okay, and the mechanism is identical to that of the one with iron 3 bromide. You just basically replace the iron with an aluminum. Okay, so what have we got now? We can do a bromination, which is a substitution reaction. On benzene, we can substitute a hydrogen for a bromine using aluminum tribromide or using iron 3 bromide. Either one will work. So we'll put here or. Either one of these works. Okay, really handy reactions. And if you're an astute student, and I know you all are, you might be wondering, well, what the hell do you do with that? Okay, well, you could make a Grignard reagent with it, right? Okay, remember Grignard reagents? Yeah, you could treat that with magnesium, and then you'd have a good nucleophile. And we're going to see other reactions that we could do with this molecule, because this is called bromobenzene. So bromobenzene. We're going to see what else we could do with bromobenzene later on in the class. So what about chlorination, right? I told you that you could do chlorination and you could do bromination. Well, the chlorination reaction is similar to that of the bromination. The mechanism is the same. However, we can use aluminum chloride instead of aluminum bromide, and again, the mechanism is analogous to that of the what am I talking about? Of the bromination. Okay. Just another point here. If you're wondering, like why aren't there any reactions that show me how to make fluorobenzene? Okay, so this would be fluorobenzene or iodobenzene. We'll talk about iodination and fluorination later on in the class, okay? But the reason that we don't use fluorination or iodination is because fluorination is so exothermic that it's really violent. It can cause explosions. And generally speaking, we frown upon explosions in organic chemistry, whereas iodination is just too sluggish. It's too slow to be practical. There is a question in our book, however, that mentions iodination, okay? And I do want to point it out to you. It's question 18.1. So 18.1. So quite literally the first reaction in the chapter. And I do want you to know this reaction. So I want you to take the time to look at this question. And it shows that you can do an iodination if you spruce up the reaction conditions. You start with benzene. I'm just going to highlight one hydrogen for instructional purposes. You treat it with iodine, but instead of aluminum iodide or iron 3 iodide or anything like that, what you use is copper 2 chloride actually, okay, and you can end up doing an iodination reaction. Okay, so that's another reaction that I want you to be aware of. Okay, I want everybody in the class to be aware of it, and I want you to take a look at question. Again, this is question 18.1, okay? And then the whole fluorination thing will wait till the very end, okay? And of course, there are other, there's other ways, but this is what you need to know in terms of halogenation, bromination, chlorination, and iodination. And then fluorination we'll worry about at the very end. Well, let's move on and get it back into our mechanism here. This is what I told you about, a few minutes ago, is that the electrophilic aromatic substitution mechanism, okay, for chlorination is analogous to that of bromination. All you do is you replace the bromines with chlorines, and you replace the iron or the aluminum, you put another aluminum in there, right? It's the same thing. The first step is nucleophilic attack by the aromatic ring on the electrophile. You form the sigma complex. Everybody should be able to draw all the resonance structures for the sigma complex. Then you show the proton transfer in the last step, which is shown here, right? Proton transfer. And then you restore aromaticity with this curved arrow right here, don't you? And then you restore the aromatic ring. Okay, so nucleophilic attack, you produce a sigma complex, then you do a proton transfer at the end. All right, and then here it goes. It says, in fact, all electrophilic aromatic substitution reactions that are discussed in this chapter, and there's a lot of them, but as long as you understand this mechanism, you'll always be able to find your way out of the woods, so to speak. You'll always be able to rationalize how the reaction happens because it's the same thing over and over again, right? Organic chemists are just like all other scientists. We enjoy patterns. And so the pattern is always this. You figure out what the electrophile is, and they're going to vary, and we're going to see other ones right now. Okay, we'll see more. But you figure out what the electrophile is, you get a nucleophilic attack, you produce a sigma complex, and then you do a proton transfer. Something that I get asked about very rarely by students, but I remember one time I taught this, and a student kind of piped up, and he said, what's the big deal with the sigma complex? Like he said, I get it, but why do they always make a point of showing all these resonance structures? And the reason why, I mean, first of all, they're important that you understand, the different resonance structures. But the sigma complex is going to come into play even more later on in this chapter. When we look at using molecules instead of benzene, what about toluene, right? Or what about anisole? Or what about, something where we have a substitution already on the aromatic ring? The sigma complex is going to play an even more important role in substitution reactions then. So just something to kind of put that bug in your ear. So what have we talked about? We've talked about bromination, chlorination, and question 18.1, which deals with the conditions for iodination. Well, let's move on. I promised you more reactions, and I shall deliver. The next one is a sulfonation. It's not a nation of sulfos. It's where we add a sulfonic acid, right? And if I draw the Lewis structure here, so that's, what is this? It's if you have the aromatic ring, and then you have a sulfur with the two oxygens doubly bound, another oxygen like this. Okay, so this is called a sulfonic acid. Sulfonic acid. It's a functional group that you need to be aware of. Now, how would you install this sulfonic acid? You use something really funky. That almost sounds like something you'd use at Halloween or something, right? It's called fuming sulfuric acid. You're like, well, I've definitely heard of sulfuric acid. I've even, probably a lot of you have used sulfuric acid in the lab. Well, now it's fuming. And what is fuming sulfuric acid? It's actually a mixture. And I've only used fuming sulfuric acid a few times in my life. But what they do is they actually mix sulfur trioxide with sulfuric acid. So it's actually sulfur trioxide, which is the active reagent in there. It's the electrophile. Okay, it even says it right here. SO3, or sulfur trioxide, is the electrophile. Now, in terms of sulfur trioxide, okay, let's just zoom in on it here. Here's the electrostatic potential map for sulfur trioxide. Remember that red represents electron density. So all the electron density is on the oxygens, right? There is like nothing here. This is really electropositive. Why is that? Well, first of all, oxygen is the second most electronegative element in the periodic table, isn't it? So you know that there's a dipole going this way, there's a dipole going this way, and there's a dipole going that way. And just that would be enough to say, like, man, you got three dipoles yanking on this thing. That thing is going to be electrophilic, right? But there's another consideration to take into account. Right, oxygen is in period 2, okay, whereas sulfur is in period 3. So when you form a pi bond, what's the overlap? The overlap is between the p orbital here and the p orbital on the sulfur. Well, the p orbital on the sulfur is I've got s orbitals on the brain, is a 3p, and here it's a 2p. The orbital overlap to make the pi bond is really inefficient. Why? Because the p orbital on the sulfur is so dang big compared to the one on the oxygen. It's just not a great fit. Okay, so the overlap is really crappy, actually, to pardon my language. So this bond actually has a lot of single bond character, okay, and most of the electron density is really on those oxygens. If you're wondering, well, why don't we consider the same thing for a carbon-carbon double bond or a carbon-oxygen double bond? Because, yeah, there's a p orbital here and there's one here, but they're both 2p's, right? Oxygen is in group 2, or sorry, period 2. So the overlap is pretty dang good, right? Anyhow, after all that, I mean, the bottom line is this. Sulfur trioxide is just a wicked, powerful electrophile. So what's going to happen when an aromatic ring gets exposed to sulfur trioxide? Here's that explanation that I just gave you, so I'll move on from there. What happens when the benzene or the aromatic ring sees sulfur trioxide? Well, since this is so dang delta plus, it's just going to be like, attack, you know, it just attacks it, okay? Just goes for it. So what happens is, after it attacks it, you end up breaking a pi bond, same as always. You get the nucleophilic attack. That was the first step. You form a sigma complex, which isn't aromatic. You should be able to draw all the resonance contributors. And then you end up deprotonating on the same carbon where the new group is. Okay? So you do a proton transfer with water, right? Sulfuric acid is a mixture of H2SO4 and water. So you have water kicking around that does a deprotonation. Then a molecule of hydronium will do a protonation to make your sulfonic acid. And there's the sulfonation mechanism. Look, same things over and over again. If you like repetition, my friend, here you go. Nucleophilic attack, sigma complex, proton transfer, done. Okay, that's it. It's the same thing over. We're going to look at nitration next. The same thing. Just a couple of different nuances, right? What are the nuances? Well, when we did bromination, we could use iron 3-bromide. We could use aluminum bromide with chlorine. We could use aluminum chloride with iodination. He showed me, you know, it was question 18.1 that I have to look at, but that was using iodine and copper 2 chloride. Now for sulfonation, what do I use? I use fuming sulfuric acid. So you actually have to write that down, that it's fuming, so the reader knows. And next, we're going to look at another reaction called nitration. But before we get to that, I want to talk about the whole concept of, you know, the fuming sulfuric acid. So fuming sulfuric acid is concentrated too, okay? It's really, you know, really highly concentrated. So you can do the sulfonation that way, but you can also remove this sulfonic acid too. How do you do that? You treat it with dilute sulfuric acid. Now, I don't have it bookmarked in here, but there's a question in the textbook where it shows the benzene sulfonic acid, and then it shows benzene as the product, and it asks you to draw the mechanism. So it tells you this, and it says draw. The question is nothing more than that. It's just draw a mechanism, okay? And you should take a look at that question. It's basically this mechanism, but in reverse. That's all there is to it. Anyhow, something to think about there. All right, let's move on to the next one. So we've covered halogenation, we've covered sulfonation, and now we're going to take a look at, we've covered halogenation, we've covered sulfonation. Now we're into nitration. Nitration means you're adding a nitro group, right? This is a nitro. One of my students told me one year, he's like, hey, check this out. I have a drink, and it was called like the nitro drink. Sorry, I'm not that on top of the drinks these days, but anyhow, he had a drink and it was called the nitro drink or something anyway. But nitration occurs by mixing nitric acid and sulfuric acid. So you actually mix two really strong acids together. I know that this summer the Organic 2 lab is only offered online with Mr. Geiger, but this is an experiment we used to do a lot in the Organic 2 lab when it was face-to-face. If you look in the shop style textbook, which I don't even know if you need to buy it this summer, but if you have a copy of that textbook, it's experiment 12.2a. And we actually get the students to use both nitric acid and sulfuric acid in the lab. Look, I worked in a lab for a long time, and I've been burned by every kind of acid you can think of. Sulfuric acid, I mean, you can put sulfuric acid on your hand. I wouldn't recommend it, but you don't feel anything right immediately. You usually just wipe it off as best you can and then rinse your hand underwater, and you won't really notice anything if you just get concentrated sulfuric acid on your hand. However, nitric acid, you want to talk about something that burns like immediately. Nitric acid hurts right away, which is kind of funny because nitric acid is significantly weaker, is a weaker acid than sulfuric acid. Nitric acid has a pK of around -1.4, so pK around -1.4, and the pK of sulfuric acid, which I'm sure you have memorized from Organic Chemistry 1, is around -9. So that means that sulfuric acid is about 10 million times more acidic than nitric acid, but there's something about the nitric acid that just burns, it hurts really bad. So if you're wondering, well, you showed me what the electrophile was in the chlorination, the bromination. You showed me the sulfur trioxide and you explained why that's an electrophile. What's the electrophile here? Well, the electrophile is something called a nitronium ion, NO2+. Now, if I was to ask you to draw the Lewis structure of NO2+, and I know that that would be a perfectly legitimate question because I've asked it to my General Chemistry 1 students many times, and they'll draw something that looks like this, okay, where everybody has a complete octet, but there's a formal charge of +1 on the nitrogen. It's the less electronegative element, right? You have 5 valence electrons, subtract 4 sticks and 0 dots, you get +1, so that's good. All right, so that's a nitronium ion. Let me show you where the nitronium ion comes from. This is the Lewis structure of nitric acid, HNO3. This is the Lewis structure of sulfuric acid. So here's the mechanism, something you might not have ever anticipated seeing in your life, right? A strong acid like nitric acid, something that's really dangerous, you know, getting protonated by another acid. But again, I told you that this is 10 million times stronger of an acid. So it protonates it so that you lose water, okay, by this mechanism, and you form the nitronium. I mean, come on, look at this nitronium, people. You've got a positive charge on the nitrogen. If that wasn't bad enough, you've got a dipole going this way and a dipole going that way. The nitronium is actually pretty unstable, okay? You've got to be careful when you're messing around with the nitronium, because if you are trying to do a nitration and it sees any nucleophile, it's going to react, okay? It is so stinking electrophilic. So you can imagine what's going to happen when an aromatic ring like benzene is exposed to the nitronium ion. Let's take a look. What do you think is going to happen? I bet it's a nucleophilic attack. I bet right. Right, first step, nucleophilic attack. There's our NO2 over there, and we have our sigma complex. Make sure that you are able to draw the Lewis structure of NO2, right? What you're seeing here is, and I'll redraw the molecule. So we have a double bond here, we have the positive charge here, a proton here, but a nitro has a nitrogen with 4 bonds, right? The nitrogen has a positive charge, but one of the oxygens has a negative charge. So make sure you are able to draw the Lewis structure of a nitro group. We have the sigma complex down here. And then what do we have at the very end? We have a proton transfer from water, which is going to be in our reaction mixture. And there you go. You restore the aromatic ring, and voila, voila, bing, bang. Now you've made this molecule. It's called nitrobenzene. So nitrobenzene. Okay. Nitrobenzene. Pretty cool molecule, a nitrobenzene molecule. All right. Now you might be wondering, what do you do with that? You know, what do you do with the nitrobenzene? Well, whatever you want, I guess. But one of the most common reasons why scientists do nitration reactions, nitro groups are pretty uncommon in like a drug, for example, unless you're thinking of like, nitroglycerin or something, you have high blood pressure or whatever. But nitro groups in a drug, are pretty rare. And I could prove that to you, but I don't have the time at the moment. So usually what nitro groups are used for is to reduce them. to form an amine, and you can reduce them using this interesting set of conditions. Now, this is a reaction I've done hundreds of times. When I was, the last job I had in Canada, I worked in a program on cardiovascular medicines where we used to make nitros and reduce them every day. And you literally take the nitro compound, you mix it with hydrochloric acid, you heat it up a little bit. There's no heat here, but you don't have to heat it very much, so we'll leave that out. And then you literally throw in some iron filings or zinc. The program that I worked in, we used iron most of the time, and it might seem like a funny thing, you know, you're like, it's kind of interesting conditions. And there's no mechanism for it in our book either. What does that tell you? It tells me one of two things. Whenever a mechanism is left out in our textbook, it either tells me that the mechanism is really complicated, right? It's beyond the scope of our class. That would be number one. Number two might be it's not really that well understood. You know, maybe it would just be a lot of hand waving and conjecture. And so some mechanisms get left out for that reason. But anyhow, we can reduce that using iron or zinc, right? We take HCl, but what's that going to produce? Well, if you do that first step, right, you don't end up with aniline. You don't end up with this. Since you're in a strong acid and this is a base, you end up with anilinium, okay? You end up with this, NH3 plus, okay? You end up with the conjugate acid of aniline. So then in the second step, you deprotonate it with sodium hydroxide, which is a base. All right, and if you did the extraction lab with me in Organic Chemistry 1, you probably know, how to separate an acid from a base, and this is a reaction we looked at in detail. So if you put everything all together, right, you put it together in a beautiful synthesis sandwich, I guess, you take your aromatic ring, you nitrate it using nitric acid and sulfuric acid, you reduce it using iron or zinc and HCl, you get the anilinium, and then you treat it with base, and then you produce the conjugate base of anilinium, which would be aniline. So kind of a neat thing. And then if you're like, well, Mr. Dion, why, you just told me, 3 minutes ago that people like to do this to make aniline derivatives. What the hell can I do with that? Pardon my language. Oh boy, all kinds of stuff. You can do all kinds of things with an amine. But later on, we're going to do an entire chapter on amines. And so we'll get more into that there. This chapter really gives you a good sense of why an organic chemist here, he has to know many reactions. There's many transformations to be covered in organic chemistry. All right, let's move on from there to the next section, which deals with something called Frito-Crafts alkylation, right? Frito-Crafts alkylation. You can guess that it was developed by two people whose last names are Friedel and Crafts. Now let's take a look here. We're going to take a look at Frito-Crafts alkylation. Then we'll take a look at a reaction called acylation, Frito-Crafts acylation. So if you think about what we've covered so far, we've covered chlorination, bromination, iodination a little bit. Question 18.1, remember I want you to look at that. Sulfonation to make a sulfonic acid, and nitration, and then the reduction of the nitro to an amine to make an aniline derivative. Well, what if I just want to add a plain old alkyl group, right? I want to take benzene and I want to make sec-butylbenzene. Okay, this is a sec-butyl group here. How would you add that? How do you take an alkyl group and render it a powerful enough electrophile? Well, what you do is you start it with the alkyl halide and you treat it with a Lewis acid, right? Aluminum chloride is a Lewis acid, right? Remember in Organic Chemistry 1, we did a whole section on Lewis acids and Lewis bases. So this is a Lewis acid. And what happens is that the Lewis acid, what's a Lewis acid? It's an electron acceptor, right? The Lewis acid is an electron acceptor. Where is it going to accept the electrons from? Well, there's 3 lone pairs on the chlorine, so it's going to accept a pair of electrons from the chlorine to form this complex here, and then this bond here can break, and what do we end up with? A carbocation. Hello, if there was anybody who ever wanted electrons, who was hungry for electrons, who was a powerful electrophile, right? If there was anything that was ever a powerful electrophile, well, a carbocation is it. He's like, give me electrons and give them to me now. Notice that you end up with this secondary carbocation, so no rearrangement is going to occur. Anyhow, I'm just going to put that bug in your ear. Well, what happens when you expose benzene to that carbocation? What do you think? That's right. Your first guess is the best one. Nucleophilic attack, right? Nucleophilic attack to produce the sigma complex, okay? And then there's going to be a proton transfer. Notice, the proton transfer, something we looked at today used water for the proton transfer. So it depends. But whenever we have the Lewis acid, aluminum chloride, or iron 3 bromide, or iron 3 chloride, we always end up with something like this that does the proton transfer at the end. So you end up making the desired compound, plus you'd also, oh, is it on my slide? HCl? Oh, yeah, it's there. So you also make HCl, and you end up with aluminum chloride. So you restore your catalyst, the aluminum chloride, the Lewis acid. There you go. So again, I mean, I know I'm repeating myself a lot, but I think there's enough work in here that it bears repetition. There's enough content here. What's this mechanism? It's that same generic EAS mechanism that we saw, 25 minutes ago. The nucleophilic attack, the sigma complex, and the proton transfer to restore the aromatic rate. Same thing over and over and over again. Well, it's not that simple with the Frito-Crafts alkylation. So, I think I might have told you this last class. I get mixed up because I'm teaching a few classes right now. But a number of semesters ago, I had a guy who sat in the back of the class who, did very well in organic chemistry, and he was had kind of a funny bone. And he used to say, you know what, Mr. Dion, I feel like organic chemistry is memorizing a lot of rules and then the exceptions to all of those rules. So Frito-Crafts alkylation has a bunch of interesting kind of little tidbits. I don't know if I'd call them exceptions, but it's got a bunch of little nuances that come along with it. So let's take a look at the nuance, okay? A secondary carbocation, yeah, we see those in organic chemistry. A tertiary carbocation, of course, okay? But a primary carbocation, we don't see those a whole hell of a lot in organic chemistry, do we? If you have ethyl chloride, okay, so that's what this is here. You can call it chloroethane, or you can call it ethyl chloride, whatever. Okay, what's going to happen when ethyl chloride sees the Lewis acid aluminum trichloride, right? It's going to donate a pair of electrons, and you're going to end up with this. Now, notice that when we had the sec-butyl, right, when we had this, that our electrophile was this, okay? Well, that's not going to happen with ethyl chloride because you're never going to form this, right? That's a primary carbocation. We do not see those in organic chemistry. So the nuance is if you have an ethyl, or if you're using ethyl chloride or ethyl bromide would work too, it doesn't break this bond, okay? This whole package here is your electrophile, okay? So your aromatic ring, in this case, the nucleophilic attack would look like this, okay? You'd end up attacking here, and then you'd break this bond simultaneously, like that, okay? Now, the thing is, if there was such thing, and there isn't, but if there was such thing, hypothetically, as an ethyl carbocation, there's no way that can rearrange, right? It cannot happen. So if you add ethyl chloride and aluminum chloride, you're always going to get an ethyl group installed. But what if you have a different primary alkyl halide, right? This would be 1-chlorobutane, and I just like to practice my nomenclature along the road, right? So if you were to try to do the same damn thing, the problem is that these are going to be susceptible to a rearrangement. So you see that you have this hydride shift the same time you get the loss of all this over here, and then you end up with a secondary carbocation. The take-home message then is that if you try to use a primary alkyl halide and you try to do a Frito-Crafts, so this is a Frito-Crafts alkylation, okay? You end up kind of with a mixture, you end up with a mixture of the primary carbocation and the secondary, and so you end up with a mixture of products. I can tell you from personal experience, there's no way to avoid a mixture. In this case, you just end up with a mixture and your life kind of sucks for a little bit until you figure out a way to separate them somehow. This is the harsh reality of organic chemistry, Setting up a reaction is easy, right? I know a lot of you took the face-to-face lab and have taken other face-to-face labs. Setting up a reaction isn't easy. It's isolating compounds, which can be very difficult. Well, I told you that there was some interesting exceptions or nuances, or what they call here limitations. You know what Dirty Harry said, a man's got to know his limitations, right? So there's other limitations to the Frito Crafts alkylation. You need to know them. I can't tell you anything more than you kind of need to memorize them, but the good news is that they make sense. The first one is that the leaving group's got to be on an sp3 hybridized carbon. Okay, if it's on an sp2 hybridized carbon, ain't gonna happen. Okay, ain't gonna happen and ain't gonna happen. Pardon my language, right? Why? Because you're never gonna see a carbocation on an sp2 hybridized carbon. Have you ever seen me draw that in organic chemistry? If I did, I must have been drinking. Okay, because there's no such thing. So delete that. Get that out of your mind. It's not gonna happen. Okay, so no reaction with either of these. You can sit here till the cows come home and beat on it, heat it up. Nothing's going to happen. Okay, will not work. Another nuance is that oftentimes we get polyalkylation. And if you're wondering, well, why would you get more and more alkyl groups being added? Right, this is a tert-butyl group. Everybody hearing the sound of my voice should know what a tert-butyl group is. Well, the problem is that after you add the first one, and we're going to talk about this more later on today, when you add the first tert-butyl group, what it does is it renders the aromatic ring more reactive. So the ring now is even more reactive. And so it's like, woohoo, not more reaction, more reactive. Okay, so now it's like, I'm ready. Now that I get this tert-butyl group, throw me another one, right? So it just gets even more reactive. Okay, might not be intuitive, but we're going to look at why. Okay, if you're wondering, why does it get more reactive, and that would be a great question, we will answer that question in detail. Okay, and let's see here. Another funny limitation, and I've seen this come up on the ACS final before. It's one of those ones that students tend to forget. I think, and when I say students, I mean everybody. Everybody tends to forget this one here and there. But it's when you have a nitro group on the aromatic ring, and there are other groups besides nitros, and I'll show you another example of something that's really what we call deactivating. This actually deactivates the ring or makes it really unreactive. So if you have a nitro group, it just doesn't work. I can tell you the quick and dirty answer, and the answer is really that the nitro group pulls electron density away so hard that this will never happen, that the ring will just never act as a nucleophile. It just won't do it. It's too resistant. Okay. Anyhow, that's kind of, the hammer and tongs approach there. Okay, with all that in mind, let's take a look at some practice problems here. It says draw the predicted expected product when benzene is treated with each of the following alkyl halides. There's 3 of them here in the presence of aluminum chloride. In each case, assume conditions have been controlled to favor monoalkylation. So we're only going to add one alkyl group. Well, if we're taking this guy, okay, the first one, so let me just draw it out like this. If we take benzene, okay, so this is A, and we treat it with chlorocyclohexane, right, in AlCl3. Remember, this is a secondary alkyl halide, so we're not going to get any carbocation rearrangement. So it's like we have this, okay, it's like we have that, and then this is going to act as a nucleophile there, and then we're going to have the sigma complex, then a proton transfer, and so the whole cyclohexyl group is going to be attached to our aromatic ring. So we're going to have the aromatic ring like this, and then we have the cyclohexyl group attached directly to it, like that. Oh, yeah.